SC spiral. Now this one, the chip and the filter inside the camera was such that it let in the H alpha light, which is what really tends to dominate the light of spiral arms. So you can see this string of reddish globs, and that is like giant Orion nebulas. Those are star formation regions, and the hydrogen gas that's not yet become stars is going to be lit up by massive blue stars with lots of ultraviolet light that is shining on that gas. So the things that outline spiral arms are things like hot massive blue stars, concentrations of emission nebulae. So this is an example of an emission nebula. So is that. So it's all these little red globs. Emission nebulae, open star clusters. Those are also places of recent star formation. Remember, open clusters don't live that long. They eventually scatter to the four winds of the galaxy because they're loose and they're not gravitationally bound all that well. Another SC spiral. Very dusty one. So again, stellar populations, these are the old stars. The blue ones are the young stars. Spiral arms, highlighted by blue stars. This again looks like it was photographed with a filter that didn't let in the H alpha light, so you don't see all the H alpha emission. It just so happens, I mean, I just got to tell you that your average camera, your Nikon camera that you have at home maybe, or your Panasonic or whatever, they put in filters, and the filters are IR cutoff filters. They cut off the infrared light. The reason they do that is infrared light is longer wavelength, and therefore by the quantum mechanics of it will focus not as well. And so to give you sharper pictures, they put in a filter that knocks out the infrared light. So that's fine for you taking your everyday shots, but they have a chemistry such that they cut off not only the infrared, but they cut off the far end of the visible red light, and that's where the H alpha is. And so if you try and take pictures of red nebulae with your ordinary camera, you're not going to see them very well. The red's going to hardly show up because of that darn infrared cut filter. Then they charge you a ton of money to replace that and put in another filter that's wider and lets in more of the red light so you can get H alpha. And then they sell that to amateur astronomy people who they figure are flush with money, and so, you know, they charge you more. Anyway, that's just another dig from Dr. Rick. Okay, SC spiral. Look at all that red. So this is taken with a camera that did not have that infrared cut filter, and now you can see the H alpha, which highlights the spiral arms. This is the easiest galaxy in the whole sky to see the outline of spiral arms and see what dominates them. What dominates them? Dust, gas, hydrogen gas, bright blue stars, open star clusters like those, and that big one. Okay, young things, sweet young things. Okay, here's an ultraviolet light picture. That's going to highlight the stars that are young even better because those are the hot stars and they give off mostly ultraviolet. A lot of dust in that galaxy. There's all kinds of pretty pictures. We could spend too much time looking at pretty pictures, but we want to get you to the key facts. Okay, barred spiral. So there's the bar. So now I'm going to tell you why we have bars. Why is this part of the spiral arm straight? And the reason is because the pattern of the density waves that are sweeping through the galaxy, they're moving through the material which itself is orbiting. And when those two are moving at the same, well, when the rotational period here is the same as the rotational period here, is the same as the rotational period here, is the same as it is here, then all these things go around with the same period. And then this is going to go around kind of like a stick would orbit, so-called solid body rotation. Not really a solid body, but it rotates just as if it was a solid body, and so it stays straight. So the real question is, well, okay, I understand that. Kind of like the way a marching band goes around a corner, where the outer guy has got to go really fast, and the inner guy has got to march with really short steps so that they all go around still being straight. That's my analogy. So the real question is, why are these so curved? And the reason the spiral arms are so curved is because out here, the rotation period is now definitely getting longer and longer as you get farther out. And that has to do with Kepler's third law, and it just happens to be the way the distribution of the matter in the galaxy is distributed. And so there are galaxies where the orbital period stays constant for a finite, reasonable length, and that's going to be barred galaxies, and that's the kind of galaxy that we live in. Some galaxies are more centrally concentrated, so you tend to see barred galaxies more as the late type galaxies, as Cs and so forth. The SA galaxies might end up being more the early type galaxies, and so then you're seeing regions here where the rotation period is about the same. Okay, another barred galaxy. This one probably looks a lot like our Milky Way. So if this really were our Milky Way, where are we? And I think the best way to describe where we are would be like right about there. We're on the inside edge of the spiral arm, the Orion spiral arm. And when we look towards the center of our galaxy, we see one part of the bar closer to us and the other part of the bar farther away. And we see the bar outlined by an old stellar population of red giants. And when we finally got good enough technology to detect red giants through the dust with good infrared cameras this far in and measure their distance, then we realized that, oh, that's a bar. And we're seeing it kind of neither perpendicular nor down the axis, down the barrel. We're seeing it kind of at a random angle, and so yeah, that's about where we are. That's us. If this were the Milky Way, which of course it is not, but it's probably quite a bit like ours. Another barred galaxy. And then this is an active galaxy. I want you to notice how bright the central core is. This is way in the background. Okay. But there's a bright, bright star-like core there. So we're going to talk about those coming up. This is the Large Magellanic Cloud again, and many astronomers think this is probably a barred galaxy. There's the bar. And the arms are like this, but the arms have been yanked off. So all we got is kind of the arm socket and the shoulder, and that's about it. And the rest has been hacked off. Cut off by the gravity of our own Milky Way galaxy, which is very, very close to this galaxy, which is why it looks so sharp and highly resolved. It takes up a, if you held your fist out at arm's length and you were in the southern hemisphere in Australia, then you could see this very easily with the naked eye. Very obvious. And this is the Small Magellanic Cloud, and it's part of what we call the Magellanic Stream. And it is we saw the Magellanic Stream when you looked at your earlier presentation on the Milky Way galaxy. And then what's also cool about this photo is that's a globular star cluster. This is in our own galaxy. This is maybe half of a Milky Way diameter away from us. This is about 3 Milky Way diameters away from us. So this is much further away. Or excuse me, this is much further away and this is much closer. Okay, and then there's a type of galaxy that is not in the Hubble sequence because they weren't seen by Hubble. They are very dim, very hard to see. They weren't discovered until the 1960s. They're called dwarf spheroidals, and so I'll talk about them by showing you a good picture, okay? So I want you to notice how sparse it is. This is not a dense swarm of stars so thick that they all merge together to make one giant fuzz. This is not tens or hundreds of billions of stars. This is maybe a few hundred or maybe a few tens of millions of stars. So why is it so sparse? And here's the reasoning. So these are very low mass galaxies. They form similar to our own Milky Way, clumps of stuff coming together, including ordinary matter that turns into stars. But the first generation of stars included some massive stars, of course, and those massive stars blew up. And when they blew up, the supernovae were so powerful that they actually blew the gas right out of the galaxy. So the raw material out of which you can make more stars got blown away, and so the star formation got aborted right away. And so the stars that you do see are the stars that got born right away, and then they shut them, it shut the whole process off. It's a very self-limiting process. The explosion just blew apart the stars that would normally be there. Okay, so they're aborted galaxies. The Fornax, Dwarf Spheroidal. So we live in a galaxy group. We don't live all by ourselves. We live in a very loose, very weak, very small galaxy group. We live, I should say, in a big galaxy. The Milky Way, that's a big galaxy. Among galaxies, we're one of the big burly ones. But we live in a galaxy cluster that is very poor. We've only got two big galaxies in our group, us and Andromeda. And then one other one that's kind of a junior spiral galaxy called M33. And all the other members of our cluster, which only has about 30, 40, maybe 50 members, are these guys, dwarf spheroidals. Barely visible. Personally, I've never seen one. I've tried to photograph them. I can't. They're so dim. You need big telescopes and long exposures. They're made of old dim stars, and they're far away. Maybe I could photograph Sculptor if I tried, but Sculptor is too far south. Okay, even whether you're talking about little guys or big guys, they're all fragile, floppy. You should not think of the disks of galaxies like frisbees. That's a poor analogy. They're more like crepes. Crepes that you have now separated from the pan, so they've got nothing to support them. And crepes are very, very easy to wreck. And that is one of the prime evolutionary things that happens with galaxies, is they suffer collisions. So that has to do with the fact that galaxies are separated from each other by only a matter of dozens or 100, something like that, galaxy diameters. Stars, on the other hand, are separated from each other within a galaxy by millions of stellar diameters. So the relevant way to think of it is how many diameters of yourself are you separated from your neighbors. That's what's going to determine the odds of running into somebody. So stars don't run into each other in a galaxy. The odds are too low. It's like two flies flying around in Yankee Stadium accidentally running into each other. The odds are pretty low. But galaxies are much bigger and their separations are much smaller, and so galaxy collisions are actually pretty common. So this one's got a disk that's clearly warped by a companion that's not visible in the photo. Looks like a big central bulge, and a disk that's clearly warped. So this is like a frisbee you left in the car on a summer day, and now it's all warped. This is a galaxy collision in process. So a galaxy has gone through the middle of a spiral, and there's an elliptical in the back, and the elliptical and spiral are right on top of each other, and the spiral disk of dust is clearly getting all messed up. This is Centaurus A, one of the strongest radio galaxies in the universe. We'll talk about that. But I want you to notice these shells. And they're not so easy to see here, but your eye is fairly good at picking them out. And if you amplify in Photoshop, you can pick them out better. And what this is a remnant of the collision, and the collision induced stars to go from their circular orbits, many of them anyway, into long elliptical orbits. And they go out, and they slow down, and then they're out here, and then they pause a little bit because of Kepler's third law, and Kepler's second law, and they slow down, and then they fall back in. But because they spend so much time sitting out here at the far end, if you just take a time random photo, you're mostly going to see them out here near the edges, and the light builds up because they're more dense at their edges, and each of these is so think of the galaxy as kind of gone in and then fallen back in and fallen back in, and each of those passages, as this kind of damps out and slowly merges together to make the mess we see today, is initiated stars to go into these long orbits that go out, slow down, and fall back in. So central collisions between galaxies gives you these shells. These shells like that, you know you've seen a collision. That's not a sideways fender bender, it's a head-on. Kind of a similar example, a mess. Actually, it's the same galaxy. We're seeing it now in multiple colors to show the different, the gas, the stars, and the dust. They all look different, but all doing the same thing, a big mess. This is a compact group. All of these galaxies are close together. That is an elliptical, this galaxy. Well, you know what? I'm not sure of that. This might be an S0. Actually, it looks more like an S0 than an elliptical. But what's the difference? An S0 galaxy has a disk, and the disk stellar density goes out more gradually. So the brightness here falls off more gradually. An elliptical galaxy, the brightness falls off a lot more dramatically. And then these are obviously spirals here. This one doesn't look disturbed at all. This one does. It's got a peanut-shaped central bulge. The disk is clearly warped. Here's another pair of galaxies. But now what about these? Are these guys in collision? And the answer is no, they're not. And you can tell because, first of all, you can tell that this galaxy is in the foreground because you can see the silhouette of its dust against the light of the background galaxy here. And this galaxy doesn't look disturbed at all, really. Spiral arms look entirely normal. If this were really as close to this as you might think in the photo, this would be horribly maimed and mangled, and it wouldn't look at all like a spiral anymore. Neither would this one. Now this one, though, does show evidence of a collision. Probably with this guy here, I'm guessing, a little elliptical. Because of this tail. See how it's like this spiral arm probably normally would want to bend around like that. But instead it's been yanked, it's been stretched, it's been grabbed onto, like stepping on a cat's tail as the cat goes by you. And this is like the cat's tail. This is called a tidal tail. Tidal because the tidal force, the stretching, due to gravity. Gravity pulls you in, but it also stretches you while it's doing that. And this is a tidal tail. And that's characteristic of a collision.